All right, so today we're going to start. It's not really new material, but if you want a new kind of application, but obviously this is going to become a little bit more complicated. Okay, it's not from the understanding, but the calculations maybe. All right, so this is on a section called Wing-Spars. Okay, and the best thing over here is just to start with an example, okay, with a simplified example, the simplest example we can, and then we move to a more complicated one. So here, the first one is idealize taper Wing-Spar. So here the new word is really taper. So let's say considering the simple case of two flanges and a panel. Okay, so here be careful with your figures. Okay, nice figures help a lot for the understanding. So let's say we have, let's see, two on top, two at the bottom. So let's say this is our panel. On each side of the panel, it will be a stiffener. Okay, or a flange, whatever you want to call it. So basically, and here will be the you can call this flange or stiffener. I like flange because it's shorter to write down. Let's say this would be 0.1. This will be 0.2. Okay, so what do we know, Jenny, about the flange or the stiffeners? Is that we always make the assumption that they're going to carry loads the axial direction. Yes, this is what is known as one force members. All right, so we can break this one, let's say, into a PC1 component and PY1 component. That makes me remember that in this course we are using for the span one's direction, we use so this is Y, XY, then should be this X, okay, but X we don't use it, so. And you're gonna have here the same thing over here. Along the second stiffener or flange, this will be P2. So this will be PZ2 and this will be PY2. Okay, let's call this angle over here. I don't usually use the angle, but some books use the angle. That's why I'm going to put them here. This will be alpha 1. This will be alpha 2. Okay, so I'm gonna write something at the bottom because I don't want to put too much on the figure. Consider the simple case of two flanges and a panel. Projected to a shear force dy and a bending moment So in here, let's say there is a moment, I don't know what color to use. Max and a shear force dy. I'll probably redo these figures. I don't want to put too much on the same figure. Okay, so we're going to look at two different cases. Case one will be flanges, but the same thing as stiffeners, resist bending moments. Okay, so all the loads. Okay, so that means that in this case, the only thing that is going to be resisting the load, the bending moment, will be the two flanges or the two stiffeners. Okay? We said that the skin that is around will not be resisting it. So in that case, we can say that PC1 will be equal to the moment X at that location divided by H, that PC2 will be equal to the same thing, mx divided by 2. Okay, so again, maybe I do a small figure here. Remember, this is Z. I mean, this is, yeah, Z. This is Y. And this is X, no? So we put this one here. That means that the moment is coming this way. So if we look at the deformation of this beam, if you think we have, this will be the shape on the side. What will be the general form of the deformation? It will be like what they call here a, due to this one, is going to deform up, no? Yep. Okay. So if something is deforming up, okay, so you have a cross section that is deforming up. The top of the cross section is in tension or compression. For example, this is deforming. I don't know if it's going to be good or bad, but you don't see anything, but this way, no? So the outside side is in tension or compression? And this inside will be in compression, okay? So in this case, so side in one will be tension or compression? It will be in compression, no? Okay, so this side will be in compression. And this side will be in tension. Okay, so this is something that you can decide to do or not. Personally, what I like to see is this, is that you just work with the magnitudes and that you put compression or tension, okay? But if you don't put tension or compression, what would be the other option that you could do? You could just put a minus sign over here, and that should let me know that this is compression and the other one is tension, no? Because the normal sign convention is, right here, sign convention. Is positive for tension, negative for compression. But again, generally, I don't like to use the signs. I like you to specify it, okay? Because that shows you that you're actually seeing what's happening in the structure, all right? Okay, so this would be case one. So in the case one, basically we're saying that the panel is like if it wasn't there, no? Okay. All right, so case two. Case two is going to be what? Panel is fully effective in resisting bending moments. Okay, so in that case, we're going to have P01 is going to be equal to the bending stress at 1 times the area at 1, the boom area. PZ2 will be equal to the bending stress at 2 times P2, where in that case, you can idealize the structure. Okay, like this, this will be, let's say this will be your flange 1. This is your flange 2, which is idealized. All right, and in this case now we're going to say the skin is effective of the panel, or the panel is effective. This is the panel. Okay. So now here we have PC1 and PC2. Okay, these are the forces. But what do we say about the flanges or the stiffeners? Is that they are only acting on the axial direction of the structural element, no? So that means that in order to find P1, we need to know PC1, but also P11. And the same thing for P2. In order to know P2, we know PC2, we're going to have to know PY2 in order to determine P2, no? Okay? So that's what we're doing next. All right, so now let's look at the vertical components. P1 and P2. All right, so this is now very basic trigonometry. So let's say we have here This is P1. So let's say it will be PY1. I mean, I can do it differently, but I just do it this way. And let's say this will be PC1. Did I put a comma? Yes, PC1, PY1. Okay, so from our initial figure, we see that there is an angle of alpha 1 created between those two ones over here. So we know this will be alpha. Okay, let's go back to the initial figure. Yeah, maybe I'm going to redo one over here. Okay, let me redo one figure. One, two, three, four. Let's see, I can do here 2. Okay, so I'm doing this figure just to indicate that this change in height over here will be known as delta y1. This will be delta y2. That distance, and then that distance if you run from here to here would be letter delta z1 equal letter delta z2, okay? Where this is here p1. And p2. So from the figure, again, this is very basic trigonometry. You can have that what? If you know PC1, okay, let's do maybe this. Let's come over here first. What would be tangent alpha 1? Will be equal to P y1 over P z1. But this will also be equal to, from this figure, delta y sub 1 divided by delta z sub 1. Py sub 1 is what? From this equation, Py sub 1 will be equal to z1 times tangent alpha 1, or this could also be equal to what? P C1 delta y sub 1 over delta z sub 1. Again, here I'm going to give you the choice. I don't like to put signs, but remember, if we say this side was in compression, really, this axial force should be pointing in what direction? To be pointed in, no? Okay, so you can write over here, in this case, this is compression. There's a reason why I don't like to put the signs, okay? It's because I think at the end you lose physical meaning. If you want it, did I put it before? Yeah, so if you want it, instead of write that, you can, if you want, put a negative sign, but personally, I'm not crazy about putting the negative sign. So similarly, we'll do the same thing for P2. So let me do here a similar figure. This will be PZ2 PY2 2. This is our angle alpha 2. Okay, so similarly, we can write tangent alpha 2 equal to PY2 over PZ2 equal to delta Y2 over delta Z2. Or we can write PY sub 2 will be equal to PZ2 tangent alpha 2, or we could write PZ2 delta Y sub 2 over delta Z sub 2. Okay, I give you both of them because it's basically 50-50. Some books like to use this notation, other books like to use this notation. I like to use this one. So for example, this one is just, if you have the data of your problem, you might know what is the geometry, no? So really, what is this? Is whatever is the change in height divided by the length, no? Yeah, and you don't need to start calculating angles. All right, the ratio should be equal to the angles, no? Okay, but I give you both of them. Okay, so the reason why I'm doing all this stuff is to find P1 and P2. So now that we know Py sub 1, PZ sub 1, PZ sub 2, and Py sub 2, we know what we can find the value of the axial forces. So the axial loads P1 and P2 are given. Instead of loads, maybe write forces because I don't want you to think it's an external, okay? But forces, maybe it would be more correct. So basically, we have basic geometry. This would be Py sub 1 square plus Pz sub prime square. This will give you the force of the axial force in P1, and similarly, Py sub 2 square plus Pz sub 2 square. Good. With this value. Okay, so with the first part over here, with the case 1 and case 2, we took care about what is going to be resisting the bending moment. So we're taking care of Mx, no? Now what's going to happen with Vy? What should be resisting Vy? Okay. This is the way this is going to be resisted by the panel and the flanges, no? Yeah, there's no other option. Okay, so let's look now at the shear force. So let's see here, now let's put here shear force. Y. Again, I'm going to do a figure. So this time, what you need to do in this figure is to really exaggerate the thickness of the flanges. Exaggerate as much as you can, okay? Okay, so there might be on negative side, but I'm just going to do everything on the same direction here, okay? So what can be resisting? Vertical force. Some of the shear can be resisted by what? Let me call it V sub P, will be by the panel, no? Correct? Now, if we look at the top, some of it can be resisted by what? In this case, we have P1 going up. And we can do up and down, that should not really matter, but if this was going up, if this is in compression, the Y component will be going in what direction? You can do it up and down, but just trying to simplify here. So it will be Py sub 1, because remember this side is in compression. This side is in tension. So in this case, we're going to have here now Py2. Okay, so like I tell you, it doesn't matter how you plot it, as long as you know what you're doing. So like always now, what do? We do summation of external forces should be equal to summation to internal forces. So what does that mean? That means that Dy, the external force, the way I plotted, if you plot it differently, is fine, will be plotted by V. Let's look at it here. All right, so, okay, let me write it down and then we stop. So we have Vy will be equal to Vp minus Py sub 1 plus Py sub 2. Okay, so now maybe here, if you want, you can do the math, but I'd rather do it this way. Why did I do this one down? Because in compression. No? So I knew it needed to be negative, no? I put over here, correct? Okay, and here I knew this one needed to be positive, no? So I kept it here positive. Yeah, but again, if you don't want to work with tension compression, you can just keep here. What is the previous page? You can just keep over here the negative side for tension and the positive side for compression, and you just put positive in everything, and then when you substitute, this will become negative, no? But I don't like doing that because you look the physical meaning. Yes.
So if you're doing the reactions, would your VP going down, or is it sort of?
If you do what?
So you have VP and you have VY, what? Should VP be going down to reaction? Or is it sort of-
I mean, it can be going down. It's just I just decided to plot everything positive in the direction. But yes, if you want, you can plot it down. Okay. I understand your question because it's the reaction from the external. Okay. So really, Vy generally will be a given value. So really here, what we're trying to find, we know Py1, we know Py2. What we're trying to find is that what is the amount of the shear force that will be resisted by the panel. So from here, you can find that V of the panel will be equal to Vy, and that's where you see it becomes created with the signs plus Py sub 1 minus Py sub 2. So in the case, as you just mentioned, very good question, that you're doing up or down, what is that going to change? Is that the math here will tell you if it's going up or down, no? It will be a different sign. But you see here, be careful. I'd rather work with tension, compression, I know exactly what's happening, than trusting the signs, because there's so many switches in signs that at the end you don't know. Okay? Okay? So now the shear force VP in the panel is known. Well, the shear flow can be determined. I'm going to go to the next page. So what I'm going to run out of space. And we're going to look at case 1. What's case 1? Or did I call it? Flanges. But again, it's the same as stiffness, resist, all bending moment. So in that case, we're going to have P, Z, what do we have? PZ1, I think we had equal to minus mx over h, and PZ2 will be equal to positive mx over h. So really for this one, we don't need to know the shear force in the web. We can learn it right away, but I'll keep it at the end. So I will do one case at a time. Okay, and the average, this is an important word here, the average shear flow is Q equal to V panel H. Which basically is what one of you asked me a while ago, is that really what is the shear flow? It's just the value of the force divided by the depth of the structure, no? That is the average, okay? You see, you want to make complicated stuff. This is what is known. This is what is done in industry all the time. Okay, so in that case, if you need to do the plot the distribution, let's say this will be B1, this will be your B2. Now this will be negative, but it doesn't matter, we're just doing an average. Oh yeah, sorry. This will give you here the shear Q. But remember that this is giving you here an H value. Okay? And H actually will be the distance here. So basically what I'm saying is that you could replace all this structure here. If you know the thickness of this element, okay, and the length and the geometry, you can substitute it by an equivalent area. That we'll see how to do that later on, okay? All right, now case 2. This time is what? I guess we call this one, the panel is fully effective in resisting bending moment. Okay, so in that case, if you remember, we wrote, I think we wrote PC1 is equal to sigma Z1, that's P sub 1, Z2 equals sigma Z2 times P sub 2. Sigma Z will be given by the expression mx y divided by I x. So this is the bending moment, the expression for the moment. The shear flow Q in this case will be equal to the expression we use, will be minus V panel divided by IXX of what? TYDS plus, let's say, the summations, if you have multiple ones of what? Of the B sub R, Y sub R's. So what do we say? This is the effect of the panel. This is the effect of the flange. Yeah, I'm going to put it just once here at the end. Johnny here is called stiffener in the United States. So in that case, if you have here B1 and B2, this is where what we have done before comes handy. In the middle, we have the neutral axis. So from the neutral axis is from where you measure the Y distance. would be the thickness of the panel. If you need to take into consideration this term, then what do you need to do, guys? Remember, you need to start from one point, go around the structure. No? Yeah, that was the plan that was long and tedious. Is that one? But if we do that, in that case, with the distribution, you will have an average value if you want a constant value due to this term, just like we had before. But this one here will give you what? I mean, in this case, we give you a parabolic because what should be the maximum shear? In the middle of the cross section. Now, what is shear? Friction between one surface and the other, one surface and the other. No? Where is the point where there is more surface on the real structure? With friction with the other one, will be the middle, no? Okay, so it's be here. You see in this case, you will see that Q is not constant. So on the previous case, maybe you can put here Q average, just put here constant. Okay, to make the difference.